For the beam and loading shown, draw the shear and bending moment diagrams and determine the equation of the shear and bending moment. So when they tell you to determine the equation, you want to do the method of sections. Well, in this case, we first want to determine the reaction forces. So to do the reaction forces, we're going to have to apply global equilibrium. So right here, I'm going to say apply global equilibrium. So when I apply global equilibrium, I'm going to have this beam, and we're going to have our loads here. Let me change color. I want to use this, and we go all the way across and make that straight, as straight as I can. And we have our distributed load. Okay? So we have our distributed load, which is W, and then we have our two reaction forces, which is here, and then we can see by inspection that there's not going to be any horizontal reaction force, so I'm not going to draw it. And then here, and I'll call this AY, and I'll call this BY. So we do the sum of the forces in the Y direction must be equal to 0, with this being positive. And so what that means is AY plus BY minus W is a distributed load, so you have to multiply by L. That's all equal to 0. And then we do the sum of the moments about, let's say, A equals 0, where this is the positive. And so what we do is we say, well, my A acts at that point, so that's not going to count. But my W is going to count, and it's going to be a negative moment, so negative WL. And that's going to be the force, but at what distance is it going to be? At L over 2. So it becomes this. And then we have a plus BY times L. And all of that must be equal to 0. So now if we're trying to find BY, what we get is a WL squared over 2 divided by L, that my Y is this, and my AY is going to be also this. And we could have done that by inspection as well. So now, because it's a symmetric distribution. So now what we're going to do is we're going to draw two lines here, one right here and one right here. And then we're going to say we're going to cut at an arbitrary distance, and we're going to draw the diagram to the cut. And then we're going to have an AY is equal to WL over 2. And then we have that distributed load going down like this. Now, your reference X can be however you want. I like to keep it from the left side, so I'll do this. But you'll see some other references as well. Now we cut, so we have internal moments and shear. So we're going to have a V1 and an M1 here. So we're going to say that our section for X is going to be from 0 to L, and our V1 is going to be what? Well, it's going to be WL over 2 minus W times X, right? And for my M1, we're going to have WL over 2 times the distance X minus WX at a distance of X over 2. Okay, so now we have to evaluate them. So V at the point A is going to be equal to WL over 2. V at the point B is going to be WL over 2 minus WL, so minus WL over 2, which, and that's going to be from the left. And then for the MA, we're going to have 0. For MB is going to be WL squared over 2 minus WL squared over 2. So that's going to be 0. So, and we generally want the moment to be 0 at the start and at the end unless we have a concentrated moment. So now we can draw the shear and bending moment diagrams here and here. So say this is my V, and we'd usually have the units, but we don't know what they are now. V and M, so I'm gonna draw a positive WL/2 here, and then it's going to go down to a negative WL/2 here, and then 0. So WL/2 and WL/2. And then you want to do vertical lines, which are supposed to be in scale, so that you could use like a conversion and a ruler to get the value. And then from here, we're gonna know that my MA is 0 and my MB is 0. Initially it's positive like that. And so here we're going to have our max, M max, which I'm just gonna write as, oh, that's something we have to find. Draw the shear and bending moment diagrams. And the equations, we found them. There are these two, the equations that they wanted. And now we can say, when is V 0? 0 is equal to WL/2 minus WX. So that's going to be WL/2 divided by W. That's going to be my X. So that's going to be at L/2. And now we put that into M1. And we say M max is going to be equal to WL² / 4 minus WL²/4. Nope, WL² / 8. And so that would be 2 minus 1, which is 1. So WL² / 8 positive. So right here, WL² / 8 would be my max moment. And that's it for this problem right here.